Parquet files. They're everywhere in the data world, and they're so common that we can take them for granted. When's the last time you asked, hey, how is it that Parquet files store my data so efficiently? And maybe you're wondering now, what is a Parquet file? Today we'll give Parquet some love and attention it deserves. We'll see how it organizes data efficiently and what we can do to make our file sizes even smaller. Let's begin. Parquet is a format to save data. One reason it's popular is that it stores large data sets into tiny spaces. Let me show you what I mean by looking at a comparison to CSV, another format for saving data. Let's run an experiment to compare these two formats. I'm pulling data from the New York City Taxi and Limousine Commission. This is a service that provides data on all the trips taken by taxis in New York City. Scrolling down, we can see that the data is organized in a monthly file, and I'm going to pull data for the month of May 2025. You can see that many of these files are in the format of Parquet. Let's jump over and start reading this Parquet file. Here I'm importing a package called PyArrow to work with my Parquet file. I'll read the file into a variable called table, and once that file is read into our table, we can see different pieces of information about that Parquet file. For example, we can look at the shape, and here we see that this Parquet file has about 4.5 million rows and 20 columns. We can also see the schema, which tells us what columns are in this table and what the data types are. If we scroll up a little bit, we can see that our first column is vendor ID of a data type int32. We could also see the date time for the beginning and end of each trip, other pieces of information like how many passengers and how long the trip was, so on and so forth. To look at the first few rows, we can slice and look at the first 5 rows. The first 5 vendor IDs are here. The first 5 timestamps for the beginning of the journey are here. Cool. This data already came to us in a Parquet format. Let's store this in a CSV format, something we're probably more familiar with, and compare the two file sizes. Here we can take our table that is in memory as a PyArrow table and convert that into a pandas data frame. We'll quickly verify that we still have our 4.5 million rows and 20 columns. And since this is a pandas data frame, we can look at the table in a more tabular format by running a head command. And we can see some of the columns here. And now we'll save this data frame, these 4.5 million rows, into a CSV file. I'll run this command and I'll wait because this is going to take a while. So we'll edit this part out and come back when the conversion is done. Okay, we're back. That took 1 minute and 25 seconds. Let's see what happened. Okay, that Parquet file we downloaded from the website, it came as 75 megabytes. And when we did the work of converting this to a CSV file, it turned into 470 megabytes. 2 files, both of them with 4.5 million rows, but one of them takes a lot less space than the other. How is this? That's what we're going to find out today. We first need to talk about how data is stored on a file, and then we can see how Parquet makes this more efficient. Think about a table. A table has rows and columns. In this diagram, our table has 3 columns and 4 rows. This is 2-dimensional data. When we save our table into a file, this 2-dimensional data has to be converted into a 1-dimensional stream, ultimately a bunch of zeros and ones. One way of doing that is by using row-based storage. In row-based storage, what happens is when you save this table into a file, each of those cells or values are stored one row after the other. For example, the values that came from the 0th row are stored first, and then the values from the first row, values from the second row, so on and so forth. CSV uses row-based storage. An alternative storage is column-based storage, and you can probably guess that here we're taking our 2-dimensional data and storing it one column at a time, meaning that when stored to file, the values from one column appear next to each other before the values of another column begin. So what? Why does column-based storage even matter? Well, think about this. Suppose you had a table with millions of rows and maybe a few hundred columns, and you need to perform some analysis on it. Maybe you need to get the total from one particular column. If you had row-based storage, then effectively what you'd have to do is read each of these cells back into your table and find the column that you needed to sum up, maybe this one here, and then sum up all of those values. But with column-based storage, all the values that you need to sum up are already located in the same location on disk. So you can skip all these other column values that you don't need for your analysis and just sum up the values that you are curious about. In this way, you scan less data, you parse less data, and you can perform your calculation more quickly. Now, if you're like me, you've heard that Parquet files store data in a columnar fashion. And that's not true. I thought that was true. But then, digging deeper, I realized it's not a pure columnar storage, like we saw here. Parquet uses something called a hybrid-based storage, which combines the benefits of both row-based storage and column-based storage. Let me show you what I mean. When we have a hybrid-based storage, we take our table and break it up into a series of mini-tables called row groups. Here, our full table has 4 rows, but we can break it up into row groups of 2, where one row group makes up these first 2 rows, and another row group is made up of these second 2 rows. Then when we store the file, we store one row group at a time, and within each row group, we store one column at a time. Let me show you what that looks like. Here, we can see that the first 2 rows appear close to each other on disk, and within each row group, we can see we're storing one column at a time. Naturally, you're wondering why. Why is it that Parquet uses hybrid storage instead of pure columnar storage? Think about what happens when your table is read back into memory. While on disk, each of the values from a column appear next to each other, and when read into memory, each of the values from a column needs to find matching values to reconstruct this row. And that can be very expensive, especially if your column is made up of many different values. Think millions of values. Each of those millions of values has to be paired with another series of millions of values to reconstruct your record. But with hybrid storage, we don't have to parse through as many values to reconstruct each record. By design, we're limiting the number of rows that are within each row group, so there's less data to scan as the data is reconstructed into a tabular format. Cool, so CSV stores data in row-based storage, and Parquet files store data in a hybrid-based storage. But there's more to the Parquet format. Here's a diagram of the components of a Parquet file, and this is pulled from the Apache Parquet website. If you look closely, you'll see we've talked about some of this already. We talked about how a Parquet file is made up of a series of row groups, and within each row group you have a bunch of column chunks. But within each column chunks, you also have something called pages, which is the most granular level of data organization. This diagram shows you a little bit of that hierarchy and structure. Near the beginning, we have our first row group called row group 0, and after that, we have another row group 1. Within each row group, we have our first column called column A, and then another column chunk called column B. Within each column, we have a series of pages. Here's page 0, and here's page 1. Now, within the pages, we have our raw data or some information about how that data is organized. At the bottom of the file, there's something called the footer, which contains information about the file itself. We can see things like the schema, or the name of each column and the type of each column, but we can also see things about each row group, like how many values are in each row group, and special statistics that makes analysis of the file more efficient. Let's go back to the terminal and check out the footer on the Parquet file we saw earlier. Let's read that Parquet file again using PyArrow, and we'll assign it the variable Parquet file. PyArrow gives us access to the information in the footer through the metadata attribute, and calling that metadata, we can see some information. Here we see again that we have 20 columns and about 4.5 million rows, but we also see some new things like the fact that we have 5 row groups and the version of Parquet that this file is saved as. We can tap into each of these row groups by looping through each row group index and seeing what information is there. In this for loop, we're accessing each row group using the row group method and then calling out the number of rows attribute. And we can see then that of these 4.5 million rows, they're kind of evenly distributed, with the first 4 groups having about 1 million rows and the rest of the rows being in that last row group. And if we wanted to get the first column chunk within the first row, we would chain together a series of methods, and we see something really interesting. So let's slow down here and look at what is in this metadata. For that first column chunk of the first row group, we can see that it's an integer of type int32. This is the vendor ID column that we saw earlier. And then we can see some beautiful statistics about this column. We see that there's information about the max and min, it's 1 and 7 respectively. We can see the null counts, the number of values that are present. And below that, we also see some things about the compression and the encodings. We'll talk about that later. And more information about how the page is organized. Cool. Now, you should be thinking, hold up, this doesn't explain how Parquet files are so much smaller than CSV files. So far, all we did is take the row-based data of CSV files, rearrange it into a hybrid-based approach, and then stick more information at the end in this footer here. That doesn't explain why the file size is so much smaller. Parquet does a few other things to optimize storage. One thing is compression. Think of times where you've had a lot of files, large in size, and you had to compress it into a smaller package. The three most common compression algorithms for Parquet files are gzip, snappy, and zstandard. Beyond that, Parquet does quite a bit of encoding to make sure that your large table is stored in the most efficient way possible. Encoding means taking the data in a table and changing its representation while it's storing at rest on your disk. We'll look at 4 encoding schemes and the benefits of each one today. But first, some data. Suppose we have a column of names of our favorite witches and wizards. We'll see how we can store this column in different encoding formats. The first encoding style is, frankly, boring. It's called plain encoding. It takes the data as you see it on your table and stores it the exact same way on disk. Meaning that if you have a value called Harry, each of those 5 characters are stored as Harry on disk. More specifically, the 5 bytes that you see in Harry are stored as 5 bytes on disk. Every Hermione takes up 8 bytes on disk. And this pattern continues for all the values in your column chunk. Now, if you have many rows in your table, this can be kind of wasteful. Think about it. Every time you see the word Harry, you're taking up 5 bytes over and over again. Every Hermione takes up 8 bytes over and over again. And this is an opportunity for some optimization. An alternative is something called dictionary encoding. With dictionary encoding, you don't store the true value on disk. Instead, you store a much shorter ID. Here we can define a dictionary where each of our original values from our table are mapped to a smaller integer value. And when we store this table onto a disk, instead of storing Harry, Hermione, Harry, we store 0, 1, 0. Quickly glancing at it, you can see that our plain encoding takes up a lot of space, but our column chunk from dictionary encoding takes up much less space. Let's check out the advantages on a larger data set. Here we're back in our terminal, and this time I will generate some data and store it both as a plain encoding Parquet file and a dictionary encoded Parquet file, and we'll see the difference in our file sizes. We'll import PyArrow again, as well as the random module, and then we'll generate a PyArrow table in memory with 10 million rows and just 1 column. For that 1 column, we'll just randomly choose a name from our 3 favorite witches and wizards. All of that will be stored in a variable called peopleTable. Let's run this, and we'll wait a little bit because we are generating 10 million records, and it takes a little bit. That's done. Let's briefly convert that into a pandas data frame so we can make sure that we do have reasonable data. Here we can see our 10 million records are distributed among the 3 names, where each name has about 3 million records. All right, let's move on to saving this large table. Again, we'll save it first with plain encoding, where we're telling PyArrow that we want to explicitly use plain encoding. We'll save that, and then later on we'll redo the work, but this time we'll use dictionary encoding. And now we can compare the 2 file sizes. Let's use the du command again. And check it out. We can see that with plain encoding, our 10 million rows were saved as 17 megabytes, but with dictionary encoding, we have 2.5 megabytes. That's a pretty significant savings. Nice. Let's keep going. Back to our data, but this time it's been magically sorted. Every instance of Harry occurs at the beginning, then every instance of Hermione, and then at the end we can see a few iterations of Ron. Using dictionary encoding like we did before, the column chunk would look a little bit like this. A series of zeros, series of ones, and then a series of twos. But this is kind of wasteful as well. Do you see any opportunities to make this more compact? One option is run length encoding. With run length encoding, instead of repeating every value over and over again, you just write that value once and then the number of times it repeats. Let's check it out for this example. With dictionary encoding, we were saying 0 4 separate times. Instead, a more compact way of writing that would be to just write down 0 and then the number of times it occurs. Or instead of writing 1 1 1 1 6 times, you could just write the number 1 and the fact that it occurs 6 times. You can kind of see how this long column chunk of repeated values is being more compactly represented as a series of pairs, where the first value represents the actual value, and the second value represents the count or the number of times it repeats. That's all run length encoding is. It works best when you have repeated values over a given range of rows. Let's go back to the terminal and check out the savings from run length encoding on a larger data set. We're back in our Python file and we'll scroll down a bit. We'll take the same column of 10 million names, but this time we'll sort those names before we create our pi_arrow table. That'll take a little bit, but when it is done, we can check out the values to just quickly verify that Harry occurs first, Ron's at the end, and Hermione is somewhere in the middle. We'll use pi_arrow to write that table into a file called peoplesorted.parquet. And like before, let's check out the file sizes. We'll run the same command again. Whoa, check that out. 10 million rows, one column. With plain encoding, 17 megabytes. With dictionary encoding, 2.5 megabytes. But with this third approach of sorting the data first, 4 kilobytes. That's 0.01% or 0.03% of these two other options, respectively. What's the takeaway here? Please, wherever possible, sort your data before you save it. When you sort your data before saving it, you're encouraging your processing engine to use run length encoding, which has remarkable savings, as we saw here. This typically works best when you have a column with just a few unique values occurring multiple times. Let's check out one more encoding style. Here we have a column of timestamps, or the number of seconds since January 1, 1970. These are typically large integer values. If you wanted to store that with plain encoding, you know that whatever integer value you see in the table is exactly how it's stored on disk. But if you look closely, you'll see that these timestamps are sorted, and the change from one timestamp to the next, it's not that large. To go from 851 to 855, you add 4 seconds, and to get from 855 to 857, you add 2 more seconds. In this kind of situation, another kind of encoding can be really helpful. It's called delta encoding. Delta encoding works best when you have a numerical column with large values, in this case, large integer values. And the way it works is this. Instead of storing all of those large values over and over again, you just store the first large value, and then after that, you store the difference that you need to add to the value that came before to reconstruct the original value. In this case, we have our first timestamp stored exactly as is using delta encoding, and then the second value is just stored as 4 because you need to add 4 to this value to get to this long integer. The third value is stored as 2 because you need to add 2 to the value that came before to get to this integer, so on and so forth. So on disk, the values look like this, taking up much less space because these numbers are smaller. Later, when this file is read into memory, the Parquet file will tell the reader, hey, these values are delta encoded. And then something like pi_arrow will add up the corresponding values to recreate the original timestamps. It's pretty cool. Let's see how it works in a larger data set. We'll create a dummy data set again. We'll import our datetime object from the datetime module, and then we'll generate a series of 1 million timestamps using our datetime_now function. Later, we'll store that into a pi_arrow table called tstable. Run that, and we can see our TS table here. It's just a series of timestamps, and we'll store this table in 2 formats, with plain encoding and with delta encoding. First, with plain encoding, we'll take our table of TS data and tell pi_arrow to explicitly use plain encoding when saving the file. Now we'll save the file again using delta encoding. The only thing that's different here is we're telling pi_arrow to use something called delta binary packed as the encoding style. This is how we tell pi_arrow to use delta encoding. Now we can go back to the terminal and compare the file sizes. With plain encoding, our 1 million rows of timestamps took up 7.7 megabytes, but when we use delta encoding, that took up much less space, just 284 kilobytes. That's pretty good. All right, we've gone through a lot. Let's take a step back and put it all together. We've gone through a few encoding techniques, and to be fair, Parquet has much more advanced optimization techniques, more advanced than what we have looked at today. But hopefully, this overview of the structure of a Parquet file and the different encoding techniques help you understand how Parquet files store data so efficiently. Most of the times you don't need to know about the different encoding styles because your processing engine, like Spark or BigQuery, will take care of that work for you. It'll look at the data and choose the encoding style that is most efficient. But sometimes you know better than the machine. And when that's true, it's helpful to remember which encoding style should be used in which circumstance. Plain encoding, just use it when there's nothing better. It's the worst option. Dictionary encoding works best when you have a few unique values that appear a lot. Run length encoding works well when you have a sequence of repeated values, typically because your data is sorted. And then delta encoding, that works best when you have large numbers that are sorted and the change from one number to the next is relatively small. That's it for today. I hope you have an appreciation of what Parquet is. It's the backbone of data lakes, making up more advanced formats like Iceberg and Delta Lake, and it's often overlooked, and we often forget how well designed it is. If you have any questions, please let me know in the comments below, and if you like what you see, please like and subscribe. Until next time, happy coding.